Hello, good day to everyone, and I welcome you again on to another episode on Moldflow tips and workflow. This episode is in continuation to the earlier, the clip that I shared with on conformal cooling comparison between a dual domain mesh using a 1D element and a 3D mesh with all 3D channels as you model it in actual. Equally like me, you would be interested in viewing the results and doing the comparison and to see which one looks more appropriate and closer to one. So with that, let's get started and review the results for both dual domain as well as for the 3D. As you can see, I have doing a comparison between a 3D mesh with all 3D part, cooling channels and the mold, and on to the right hand side I have a dual domain mesh with the 1D element and mold model as the 3D part over here. Okay, and then what I did is I ran an analysis cool FEM. Yes, of course we are doing all comparison for the cool FEM, and I kept the the process parameters all same, and instead of like mold temperature options, I have like an average within the cycle, transient within the cycle, and transient from the startup. For the comparison purpose, I use like an average within the cycle, but you can always try doing it a transient within the cycle, which will further close up the gap, because that each after the iterations, each after the cycle, or I would say each of the steps, the results have been computed and taken forward over there, whereas in the average it's average at the end of the cycle for all the results. So there could be a little gap when we are doing an average within the cycles when two type, but let's see how much is this gap and whether these gaps make any sense for us. And let me show it what I did it for the 3D part in the process parameters. So yes, I use the average within the cycle, and I use the injection, packing and cooling time all together as cycle time of like 20 seconds and mold open time of like 3 seconds. So with that, probably let's get started with this. For the understanding purpose, I cut the part and so that I could able to see the mesh clearly. Also you could also do the as per your convenience. So let's first get started with the results that I would like to view is the log, and the most important thing is that how much time it has took to run the analysis. Well, this with the 3D mesh average within the cycle for the mold temperature, it took like 1 hour and 16 minutes versus dual domain with 1D element with the 3D mold mesh, it hardly took 3 minutes to run that. That was pretty quick. So the question arises, why did I took like 20 seconds, why not 18 or 20? Well, I did multiple iterations before I showed it to you, and I could see that 20 seconds looks appropriate. And how do I found it out is not running an automatic analysis, but I tried computing it. Well, simulation is all about computing. You have to give a try multiple times till you are satisfied with the results, and the best way would be like trying with an dual domain mesh with just like in 3 minutes, which was able to get me closer to the actual cycle time. I hope you understand that why I always prefer going a simplistic approach rather than putting a simplistic workflow. I would say when I say the comparison between the two is that sometimes people like to import everything and get started, but the analysis times it takes a lot of time. So probably if you are a professional, you have to show your skills the way you are representing the model to the solver, not the way like anyone who is getting started and pushing everything to the solver and let the computer solves for you. I would say that would not be a good approach. I hope you agree with me. And so that's the reason I always prefer to put it in a simplified approach where you show your proficiency, your professionalism of representing the model to the to the solver. So another thing that I like to highlight over here is the comparison between a part surface temperature minimum and max and average between the two of this. And as you can see that I'm not saying that they are like exactly matching, but pretty much they are very close to, like 107.5 versus 108.9, almost, or 1.5 degree difference I would say between these two. And the average is also like say approximately of like 4 degree difference on there. So this is not the very huge difference you will be able to see. And as I told you that if you try to run a transient analysis, this difference will further go down. And many of the times the question has been, how much is the heat that is being extracted out of the cavity, and you can see that the heat that is being extracted out of the cavity is like 4.2 kilowatt. It's approximately the same what we will be able to see. So in short, what I'm trying to say is that a simplistic way of representing it will a little bit compromise on the accuracy, but look at the time, computation time that you would save in terms. And particularly when I say when big models are there, this is a simplified model. If you have big models, then probably the time consumptions would be much larger in this case. Okay, so let's go and view the results. For the most important thing that I always refer to the first results is of course looking at my part average temperature on this one. Okay, and let's look at the part average temperature and for both the one. Okay, and I want the part average temperature to be below the ejection temperatures for the given resin. So in this case, for this generic HDP, generic shrinkage characterized material, looking into the processing parameters, it has ejection temperature of around 102 degrees centigrade. So in this case, probably I would say that if I do a query of this, almost like all the parts is having a closer closer to the ejection temperature, but I want to go and do a scale down and see that whether everything has been cooled down below the 102. So apply it, okay, for this as well, and scaling specified 0.02, and pretty much you can see the difference is almost the same. I would not say very exactly matching, but they are like 99% very comparable to this one actually. And the computation time for this dual domain, it hardly took like for 3 minutes versus the 1 hour. And of course I would need a little further increase in my cycle time so that this little bit increases further and I could able to cool most of the part area over here. The other thing that I want to look out over here, there's a difference in the results as well. In dual domain probably you'll get a more results like circuit flow rate, which we have in circuit pressure, and then heat removal efficiency and those things, which probably a 3D will not have in detail. But one of the important thing I like about the 3D is to look at the velocity through the channels. Actually this will show you a very systematic way of where there is a deviations or the drop in the velocity, where the velocity is moving very fast. So those areas where you are looking for a stagnation, or those things, probably 3D will give a much realistic approach or so. And that's the reason I told you that at the beginning, if your cooling channels are too complicated, that has a very organic shape that cannot be represented with the help of 1D element, then it makes sense to model that with the 3D, because that will help you to understand those dead zone areas, the areas with the velocity is dropping down, and the areas where the velocity is rushing very fast suddenly. So those things can be very much be captured with the 3D mesh or the 3D channels, where little there would be a lag into the with the 1D element also. Yeah, it shows pretty much like very certainly it's uniform. It doesn't show any change in the velocity, though there would be a velocity change happening into the channels also. I leave it to you, so you can refer to the other things like the pressure drop and those things. Probably it's almost like in this case it shows a pressure drop of around like in 1.4 MPa versus this is like in kilopascal, so a little bit of pressure drop difference will be observed between 1D element and the 3D mesh over here. So that was pretty much what I have to show it, and you can of course look at the other results like the temperature mold averaged, and let's begin with this as well, the temperature mold average. I need to on the half one. So pretty much you would be able to see the very similar behavior what we have seen in the with the dual domain also. It's the difference is because I have used a little smaller height of the mold in the dual domain versus the 3D little bit has a drop of the area of those temperature changes also is pretty much same in this one. So I hope you understand. So I would suggest that you a simplistic approach wherever possible, use a dual domain and 1D element. It will run the analysis much faster compared to the 3D. But again, if your channels are too complicated which cannot be represented with the help of the 1D element or so, I would recommend going with the 3D elements, and results are quite comparable even with the average, and with the transient they will further closely match it. I hope these 2 episodes was helpful for the conformal cooling, so don't get too much messed about it, confused about which mesh to use, when to use. Probably these episodes will help you to get clarifications on that. So with that, probably I wish you all a very happy new year ahead, and all the wishes come true, and I hope like me you would be also making a new year resolutions as well. So all the best wishes for that, and I will talk to you in the new year. So with that, stay safe, and talk to you again. Thank you.